Hello Rutuja. So, do you know that how many people were there in the that is the virtual drive?
Sir, many of them were there. Actually, even I was there.
Okay, that completed or not?
I don't know about others, sir, but I'm done with the interview.
Yeah. Okay. 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 So, we'll start our session. Uh, okay. So, in the last lecture that we start now we are about to complete the unit number 3. So unit number 3 is related to the distributed snapshot. Okay, and you know that now you have some clear understanding what do you mean by the distributed snapshot. Okay, so in the first few lectures that we have seen what exactly the meaning of the snapshot is, then the global state of the system. So how to record the global state of the system? Global state is nothing but the collection of all the local states of the nodes. So what is a local state? So local state is nothing but a state of a particular process. So there are so many processes are running in a distributed system or in a distributed application. So you have to record the state of the processes. So whenever we have to record the state of the processes, then at that time there are the certain primary things that you should have to understand, that what exactly the state of the process. The state of the process may be the active or maybe it may be idle. Okay, and it may be in other cases the state of the process may be halt, the state of the process may be um, uh, maybe idle. Okay, means active, idle and halt. So in some cases we have seen some example in the last few lectures that what exactly the local state and how, what do you mean by the consistent cut. Okay, so in a timeline, in a physical time, in a timeline there are the processes which are running. Okay, so there are the some of the processes which are FIFO ordered, some of the processes are in non FIFO order. So there are the certain algorithms who works on the FIFO order processes. There are the certain algorithms which work on the non FIFO order processes. Okay, so in the last lecture we have seen the termination algorithm. So what do you mean by the termination algorithm? Now there are the several processes running. So the state the application should know, or you can say that the coordinator node should understand to know that when the process end. So that's why there is a concept of termination algorithm. Okay, before that we have seen one algorithm. That algorithm was, one second, that algorithm was uh, yeah, Candy-Lamport algorithm. Okay, so in the Candy-Lamport algorithm, the two types of the algorithm was there in a Candy-Lamport. One is a FIFO base. So Candy-Lamport algorithm is used to record the state of the system in a FIFO, in FIFO order. And there is another algorithm. That algorithm is a wave algorithm. Okay, sorry, ELANG algorithm. That ELANG algorithm was used in a non-FIFO channel. So you must have to understand what exactly the Candy-Lamport and what is a Li-Yang algorithm. Okay, how to record the state, how that algorithm works. Okay, so the concept of the Candy-Lamport is nothing but a marker. So first of all, you have to understand what is a marker. Okay, then after that you have to understand what exactly when the marker is to be used. Okay, so how the processes are arranged in a graph. So you have to represent all the nodes and the processes of the running which on the nodes in a distributed graph. Okay, directed graph. Okay, in a distributed system. So whenever initially the processes were white, and after that when any action is to be performed, then automatically through that particular channel the marker is to be sent, and the next process will be the red process. So in this way the processes are marked by the marker, and the state of that particular node are recorded. So this is in case of a FIFO channel. That is the case of the Candy-Lamport algorithm. In case of a Li-Yang algorithm, the white processes are marked by a marker are turning white only, and the red processes which are sending the marker are turning red. So when we understand that, we have to differentiate this is just an example in the directed graph. Okay, and the directed graph, the age is nothing but a channel. Okay, so you have to record the age also. You have to record the age also. So there was one example that we have considered in the lecture, that if someone want to deposit a money. Okay, so when the someone want to deposit a money, so the first of all, what is the state of that node who want to deposit? Whatever the amount is initially, suppose that the total amount in that account is equal to 1000. Okay, so whenever someone want to deposit the money, that state of that node is equal to 1000. What is the state of the channel? Empty. And what is the state of the another node to whom that is to be transferred? Is again empty. Okay, so now after that, whenever the node sends the money, that first node sends the money to the second node. Okay, so if 100 rupees is to be sent, then what is the state of that first node? Is 900, because 100 rupees is sent. And what is the status of channel? Is 100, because now currently through the channel we are processing the request. So the status of the channel is 100. And what is the status of the next end, the other end? That is again empty, because still the process is not completed. So in this way we are recording the state. So this is an example, and real time, these are all the examples which are currently now you can understand in our all the uh, real examples that we are currently using in day to day life. Okay, so every example you can take any online application, you can take any example which have such scenario where you execute a request, and the request is still is to be completed, and you will after some time it gets completed. So all these are the states that is to be recorded by such algorithm. And it is when it is useful in a distributed system, they are very useful, because at any point of time you don't know that what to be happen next. So definitely all the states to be recorded, and the mechanism is to be should be there. With every distributed application, such mechanism should be there. Okay, that is called as, again we can say, it is a provision made by the programmers to record the states. So whenever we implement such type of the application in a distributed network or on the internet based application, you must have to consider the logs. Okay, you must have to know that how to record the states, which algorithms to be used to record the state. Okay, so it is as good as the log. So you know that whenever you are doing something, and the logs are automatically generated, your logs means what? Whatever the actions that you are whatever the inputs that you are taking, whatever the actions are generated, whichever the task that you are performing, everything is recorded in a log. Okay, so if you know the browser, so browser is also recording the history, everything, every action that is being performed on the browser, that is being recorded in a history. And similarly, it is also very good practice for you also to record such type of um, um, uh, events, such type of the logs for that particular application. So it is very useful. You have to think of that how we can keep the record of your application. Okay, so now so these are the things that we have seen in the unit in this particular distributed snapshot. Some algorithms, wave algorithm that we have seen now. Today uh, we'll see that what exactly the 1 second, just okay, just a minute. Now I request everyone that you should be responsive. You should be attend the lectures in a way, in an interactive way. So I will ask you some questions. Okay, now today that I think our third unit will be will complete, and uh, in coming Friday. So on Friday that we can uh, conduct the test. Okay, so uh, Friday there will be the test on unit number 3. So the point that I want to discuss, that is related to the distributed deadlock. So some points are remaining, just I would like to finish that point. So I think I have discussed this in the last lecture also, that is a distributed deadlock. Okay, so in a distributed deadlock, okay, so what exactly the distributed deadlock is? Okay, so you know the example of the deadlock. I think my screen is visible to you, yes or no?
Yes,
Yes,
sir.
sir.
Okay, so you know the deadlock in an operating system. Whenever whenever there are the n number of the processes are running, then there are the several resources that may be shared. Okay, several resources are shared. So in an operating system, that you know that the mutual exclusion is the mechanism that you have to apply, so that exclusively the process will get the access until the time the other process has to wait. Okay, so these are the concept and these are the mechanism that is to be applied in a environment. Okay, so now why then the deadlock happens? So deadlock is happen because of certain reasons. Okay, so every time if the algorithm not work, if the processes are not managed, then at that time definitely the shared resources. And so what is the deadlock? The meaning of the deadlock, last time I asked the question, the meaning of the deadlock is the processes has to wait infinitely. Okay, there is no limit in a time limit, that how much time that the process has to wait for a particular resource. And when one process is one process is holding the resource, he that process is not releasing that resource, other process has again holding the some resource, again that is not releasing the resource. That process is waiting for someone, other process is waiting for that, then the next process is waiting for. So it is nothing, it is like a loop. Okay, and when there is a circular wait condition, then at that time the deadlock may happen. Okay, so I think these are the example that you know that how the deadlock is happen in case of a distributed system, sorry, in case of a operating system. Similarly, here also there are the deadlock in case of a distributed system. So in a distributed system there are the two types of the deadlock is there. The first is the resource deadlock, and the second type of the deadlock is a communication deadlock. So what do you mean by the resource deadlock? Resource deadlock means, now here I don't have any diagram to show you actually, But now assume that there is one process, okay, and the one process is communicating with the many other processes that you know, okay, and similarly the one process may request for the many number of the resources. It's not only one single resource but the many resources, okay. Then now it is a distributed system. So in a distributed application, that you know that how vast it is. It depends upon your application, the scope of your application, but still you assume that there are the n number of the processes, and there are some resources, and every process is requesting some resource. So then at that time definitely there may be the deadlock that may happen. So that is the case where that is called as a distributed deadlock. Sorry, that is called as a resource deadlock. Then another type of the deadlock that may happen in the system is a communication deadlock. So what do you mean by the communication deadlock? Communication deadlock means what? When the process communicating with the any other process in a system, then at that time that process will not respond to the process who is requesting, who has requested, okay. So in that particular case the process may wait for the answers, okay. But this particular communication is uh, uh, not only for a single one to one. It is not a one to one communication in case of a distributed system. Distributed system, it may have an many communication. Many means one to many communication, means one process can communicate with many number of um, processes, many processes in a distributed nodes on the distributed node. So this particular the chances to happen the communication deadlock is very less, okay. Why very less? Because in that particular case at least one process may respond to the no to the request that is being sent by that resource, that process, okay. Means for example node number 1 is sending the request to node number 5, 7 and 8, okay. So the 5, 7 and 8 may be busy at that time, at the time of communication, if node number want to communicate with the 5, 7, 8. So the 5, 7, 8 may be busy, but at some point of time maybe 5 may get free, and then that process will respond to 1, okay. So there are the chances that the 7 and 8 may not get the access or may not response, okay. So in that particular case at least 5 fifth number processes has responded, okay. So that is related to the communication deadlock. But here what happened, the response time, or you can say that the execution of the overall system will be hampered because of because of because of because of some processes are not requesting, okay. So here that is called as a distributed deadlock. So for that and here there is a no solution actually. In case of a distributed system only there is a detection, will be the prevention, and then there may be the avoidance, okay. We cannot actually reduce, we can reduce it, but we cannot exactly do the final solution that how the processes may get solved. But at some point of time the but here one good thing is that in case of a communication deadlock at least something is happening, at least there may be the delay in the final execution to get the final output, okay. But it should not be delay should not be the case as we have seen in the resource type of a deadlock, okay. In case of a resource, the if the process is not received that resource, then we cannot then at that time no result will be come out, because without getting that resource nothing will be done, Okay, so these are the two, and now you can assume that resource deadlock is a deadlock of the type of and that the and symbol in our programming language. And means you have to get you have to get both the things, this and this, then only you can move ahead. Okay, but that is not the case in case of the communication deadlock. In a communication deadlock, it is like a or. Okay, or means why, what is the meaning of or? Means if you are not getting this one, either you are getting that one, either some of the processes out of 10 processes, the 5 processes are responding to you. Okay, then it is your work will be done, get done. Okay, then at that time you will get the output. Okay, so that is the concept which are related to the deadlock. Now here some of the things are mentioned here: centralized approach, distributed approach, and hierarchical approach. So last time that we have discussed this already. Okay, now today that there is a next point which are related to the next algorithm, that is a leader election algorithm. Now the leader election algorithm, I think we have seen the election algorithm in the previous unit. Okay, so what do you mean by the election algorithm? Now I think everyone knows that what is the election algorithm. I think most of the people, you know what is the election. So election, the meaning of the election, you know that uh, you have to elect someone, okay, from the group of people, as you know the general election. Okay, now we have some GS and JGS election. So now you know that from the group of people who are the candidate people, and from the candidate people we have to select anyone. Okay, so that is called as a election. Now second thing, now in case of a distributed system, what is the election? You know the coordinator node. Okay, so there is a one node who will be act as a coordinator node. So in the last unit we have seen this. Ricard Agrawala is the one of the um, algorithm. In that case we have seen. Similarly there is a Bully algorithm was there, ring algorithm. So Bully algorithm and the ring algorithm is used to elect the coordinator. Okay, coordinator node. So now why the election is important? Why the election is important? How it will be how it will be takes place? Because in case of a election algorithm, there should be the one node who will monitor the all the actions. Okay, all the actions that will be take care, all the action that will be uh, happening in the system. Okay, so monitoring should be done. So that's why there is a concept of election in case of a distributed system. So then who will be the leader? How you do the election? What is the method of election? So now you know what is the method of election. In the last unit we have seen uh, whenever the any node get failed, whenever the any node means whenever the coordinator failed, then at that time any process in that application can start the election process, and then the message is sent by that particular process along with his ID. So what is an ID? So every process has the ID. Okay, so we will go I will just read out it what exactly it is. In a distributed algorithm, leader election is the process of designating a single process as the organizer of some distributed among the several computers. Before the task is begun, all the network node are either unaware which node is served by the leader. because initially you don't know. Okay, initially you don't know who will be the leader. Okay, then at that time after that the election will start. Okay, then unable to come. Okay, so before the task is begun, all the network node are either unaware which node will serve as a leader, or the task are unable to communicate with the current coordinator. After the leader election algorithm has begun run, however, each node throughout the network recognizes a particular unique node as a task leader. The network node The network node communicate among themselves in order to decide which of them will get into the leader. Okay, and then get into the leader state. For that they need some method in order to break the symmetry among them. So what is the method? For example, if each node has a unique comparable identities, then the node can compare their identities and decide that the node with the highest identity is the leader. So there is a concept of identity, and every node, in case of a distributed system, the identity is assigned to every node. It may be because of some are the priority nodes, some may have and some higher priority, some may are some processes may have and more importance than the any other processes. So I am so it depends upon the identity of that process. So identity of the process may be 1 2 3 4 5 6 7 up to the their priority. So it is a number which will be assigned to each process, which will act as a priority. So the network node communicate among themselves in order to decide which of them will get into the leader state. For that they need some method in order to break the symmetry among them. For example, if each node has a unique and comparable identity, then the node can compare their identities and decide that the node with the highest identity is the leader. The definition of this problem is often attributed to the Lalem, who's finalized it as the method to create a new token in the token ring network in which the token has been lost. Leader election algorithm has designed to be the economical in terms of mm, uh, the algorithm suggested by the Galler, Hablet, and the Spira for the general undirected graph has had the strong impact on the design of the distributed algorithm in general and won the Dijkstra Prize for the influence in the paper. Now we will see the definition. The process of the problem of the leader election is for each processor. Eventually to decide whether it is a leader or not. Okay, subject to the constraint that exactly one processor decide that it is the leader, the algorithm solve the leader election problem if the states of the processes are divided into elected and non-elected states. Once elected, it remains as elected. Similarly, if not elected, in every execution, exactly one processor becomes the elected and the rest determine that they are not elected. A valid leader election algorithm must meet the following conditions. So termination. So termination means the algorithm should finish within a finite time once the leader is elected. So you know that what do you mean by the election algorithm. So when the termination occurs, okay, so it should be the finite time. You must have to decide, the process should itself be decide that they have to finish in that finite time. So that is the one of the property that may have to that must have to follow. Then the uniqueness, exactly the one processor that consider itself as a leader. Okay, so that is the one of the property, that condition that they should have to follow. Then the agreement, all the other processes knows who is the leader is. So that is the agreement. So these are on the basis of these three conditions. The overall process of electing the leader is to be performed. The algorithm of the leader election may vary in the following aspect. First of all, the communication mechanism. The processes are either synchronous, in which the processes are synchronized by the clock signal, or asynchronous, where the processes run at arbitrary speed. So now, synchronous and asynchronous. So now we have discussed this concept of synchronous and asynchronous in the first lecture, first 2-3 lectures. In that we have seen that what exactly it means. So it is a communication mechanism. Either the communication mechanism will be synchronous mechanism, okay, or it will be the asynchronous. In case of a synchronous mechanism, the physical clock of the processes of the nodes are in a synchronous manner, and in case of a asynchronous network, we are considering the logical clocks, okay, and we are considering the events, and we are considering the ordering of the events as per the in a logical time frame. Okay, means one event is occurring after another. Some of the events are concurrently happening. Then for that purpose, the another algorithm that we have seen. Okay, so that type of the assumptions, that type of the algorithm that we have to use in case of the communication mechanism. So the first of all, the communication mechanism, the process name, whether the processes have the unique identity or distinguishable, that is the anonymous. So every process has an identity, okay, and accordingly they are working. Okay, so I think you are getting this concept. Then the network topology, either it is a ring, either it is a acyclic graph or a complete graph. Okay, so you know that how the network is there. So whenever we are considering the ring, so what does it mean? The nodes are connected in a ring. It's not like that. Okay, so they are all according to your logical execution of the processes. So logically the ring, so in one algorithm, in case of a Ricard Agrawala, in case of the election algorithm, coordination Bully algorithm, we are consider that the nodes are logically connected by a ring. Physically they are not connected in a ring, so that you have to first of all understand what exactly it means. Okay, so whenever you are performing any problem, whenever you are solving any problem in a distributed system, you have to think in the way that how the algorithm is constructed. Okay, if algorithm is related to the logical execution, then at that time uh, actually it is not present whatever the sequence, whatever the things which are described in the algorithm, all the concepts are related to some execution, all the concepts are related to some assumptions, how how the things to be done, how the things are executed in the network. Okay, so here network now, but basically for this particular case, for in this particular case, for the election, here the network topology may be ring, the network topology may be a cyclic graph, or network topology may be the complete graph. So I think you are getting the point that I am trying to say. Okay, now the first is that the leader election in ring. So now this is the ring network that you can see on the screen. Okay, so this ring, so you can see the ring topology. So how it works? So just for a second, I want to execute one video that you I think you will understand what exactly. So just so we are going to now describe about the ring topology. So in an oriented ring, processors have a consistent notion of left and right. So for example, this particular diagram, which is illustrated over here, you can see the processors P0, P1,
P2, P3 and P4, they have P0 and P1, they have the channel. So P0 is connected to P1. On the left side, it is numbered as 1, and P1 is connected to P0 with a number that is 2, that is called the right side. So if we see all the numbers as 1, then the orientation of the ring is basically nothing but the orientation of a ring is a clockwise. So if we basically keep on navigating over the number 1. Similarly, if we are navigating over number 2, that is P0 is basically communicating with P4 and P4 is P3, that is through the number 2, then basically it is a counterclockwise. So this is called oriented ring. So orientation of a ring can be basically formed using this numbering of a channel, and that is to be done by the processors at its own level, that is a local level with a local knowledge. So for example, if the messages are always forwarded on a channel 1, they will be cycled clockwise around the ring. So why we study the ring? Because in a message passing system, which is basically used as a ring structure or a ring topology, gives a starting point and also easy to analyze the algorithm and design the algorithm and ring also. So, and the lower bounds and impossibility results for the ring topology also applies to an arbitrary topologies. So whatever algorithms we are designing in this particular setting can also be applied as well in arbitrary topologies. So the different kinds of rings we are now going to start and discuss. The first type is called anonymous rings. In anonymous rings, the processors do not have the unique identifiers. That means all the processors are anonymous, and thus the ring formed out of these processors without having the same state machine. And also the algorithm relies on knowing the ring size, that is how many number of processors are there. Then there is another kind of ring structure, and that is called basically a uniform ring. So uniform ring will have n nodes, but this particular number of nodes are not known, then it is called uniform, because all the processors are now uniform. The algorithm which uses this information, that is without knowing the ring size, called uniform algorithm. So uniform algorithm does not use the ring size. Formally, every processor in every size ring is modeled with the same state machine here, and that is why it is called uniform algorithm or uniform ring structure. A non-uniform algorithm uses the sizes of a ring in the algorithm design. So formally, each value of n, every processor in the ring of size n is modeled with the same state machine, that is of an. So that means for a different ring size of value n, different algorithms or different state machine will represent by an. Now we are going to see if the ring is anonymous, that is the unique IDs are not given to the processors. So about in this particular setting, about the structure, that is a ring leader election algorithm, how it will work in this particular setting. So there is a theorem which says that there is no leader election algorithm for anonymous rings, even if the algorithm knows the ring size, that is if it is non-uniform, and also it is basically following a synchronous model. So this result is called impossibility result. That means no leader election is possible if the ring is anonymous. That is, if the IDs are not given. We are going to see the proof, and then this impossibility results will be used in as basically a information to develop the leader election algorithm. So the proof sketch goes like this. Every processor now begins in the same state with the same outgoing message, since they are anonymous. So every processor receives the same message, does the same state transition, and sends the same message in the round 1. Now you may ask, if a processor is sending the message to whom it is sending, how it will know to whom it is going to send, or that who is the destination. Then you have seen that the channel numbers, that is, if it is oriented ring, that means if it is a clockwise, then it will always basically send to the channel 1 and so on. So basically the channel numbers will be used instead of if the IDs are not known. And this particular structure will represent the same state machine. So same message will be transmitted and same state transition will happen after the receipt of a message. So eventually some processor is supposed to enter in an elected state, but then all would enter into an elected state. So in this particular setting, if we analyze using the safety property that never elects more than one leader, here every node is elected as a leader, or liveness eventually elect at least one leader is also violated. So in this particular proof, we have seen that there is no leader election algorithm for anonymous rings. Now, since we have proved this theorem since the theorem was proved for non-uniform and synchronous rings, and the same result will hold for a weaker models. Weaker models in the sense, if it is uniform means the value of n is not known, and also a weaker one that is called asynchronous timing model, then also this particular theorem holds and leader election is not possible for anonymous rings. Now we are going to discuss the rings with IDs, because if the leader election is not possible in basically the anonymous rings, then we are going to consider the ring structure with the unique IDs. So IDs are assigned out of the natural numbers, and so each processor has a unique ID now. So now we are going to discuss about that IDs, how the IDs are assigned. So specifying a non-anonymous ring where each processor is assigned a unique ID is illustrated in this particular diagram, and I will be explaining you through this particular example. So start with the smallest ID from here. Smallest ID is 3. So let us note down this particular ring in this manner and list IDs in a clockwise order. So clockwise order goes like this. So first ID is 3, then the next ID is 37, and furthermore the next ID is 19, then 4, and finally 25. So just see that this particular structure, if this rule is followed, then it will give a oriented ring. And this will be a non-anonymous oriented ring structure, which we have seen as an example, and this particular structure will be used to design the leader election algorithm. So non-anonymous algorithm, if it is uniform, that means there is one state machine for every IDs, and no matter what the size of the ring. That means the algorithm in this particular setting does not know the size of the ring, that is n is not known. Non-anonymous, it knows the value of n. There is one state machine for every ID and every different ring size, and basically it will form a non-uniform, non-anonymous algorithm. So these definitions are tailored for leader election in the ring. So now we are going to discuss the first leader election algorithm with the message complexity of the order n square, and this algorithm is called Leland-Chang-Robert algorithm, that is LCR algorithm. So it's the simplest algorithm, and it will give the start point to understand the leader election algorithm design in a distributed system. So here every node, every processor will send the value of its ID to the left in a form of a message. So we can see this particular example. So every processor will have the IDs, and that is unique ID because it's a non-anonymous ring. Now send the value of its ID. So it will send a message with its ID 0 to the left. Similarly, this also will send, and everyone will send its values. Now when an ID j here from the right it will receive the message, and if the j, that is the ID of incoming message, is greater than its ID of a receiving process, then it will forward to the left. Here in this case, this situation is not considered, this situation not happening. The second j is equal to ID, that is also not satisfying, and if j is less than ID here, then it will do nothing. That means 0 will not be, this particular message will be swallowed. And this particular structure will go on. So you see that in this structure here, this will also be swallowed. This message will be swallowed, this message will be swallowed, but this will continue, and this again will be continued over here. So two message of size 2 will continue over here again, and this will also forward it. So 2 will come again over here from where it is being originated. So the correctness of the algorithm goes like this, that it will always elect a processor with the largest ID, and the message containing largest ID passes through every processor and basically comes over here again. As I told you, the message of a processor ID with the highest ID will goes along the entire ring and comes back to it, and it will be elected as a leader. And all other nodes, then after electing a leader, it will send a message that is called termination message, and all other nodes will become a non-leader. So the time which is taking here in this algorithm is of the order n, and the message complexity, if we analyze, it depends on how the IDs are arranged. So the largest ID travels all around the ring, that is, it will basically result into n different propagation of the messages. Second largest ID will travel until reaching the largest one. Third largest ID will travel until reaching the largest or a second largest, and so on. So we can understand using this particular example the message complexity, that is order n square. So just see that here the ID that is the highest ID, that is the ID which is number 4, will be propagated along all the ring and will come back over here again. Similarly, the second lowest ID, that is 3, will propagate, and it will not pass through P4Y because it is having the highest ID. It will swallow this particular message. So this particular messages are being flowing. So if we count how many messages are, total number of messages is being flown, you can see that the highest ID will basically result into n different messages. Next largest ID will have n minus 1, n minus 2, and so on up to n. So if we sum up, it will become the n square. So this particular topology will incur into n square number of messages. So that is why the message complexity of this algorithm is of the order n square. So we go of n square. That means this particular topology, this example of a topology we have seen where exactly n square messages are required. Maybe in other topologies it will require even less than n square, but in no situation the number of messages will exceed n square, and that is why this particular diagram, that in any admissible execution it will send never more than order n square messages. That is written over here. Moreover, there is an admissible execution
Okay, so now I think you understood that what exactly the ring topology in a synchronous and asynchronous network in a distributed system. So leader election algorithm, the way that it is explained, that from the left to right in a clockwise direction, the ID is sent along with the message. So those processes which have ID higher than that of the any other messages, that will be get circulated among the ring. Okay, and the lower id is get followed by that particular node, and the highest id will be sent along with the messages. So in this way that particular message will come across with every other node in the ring, and then again it will come back to the original state, original machine, original node. So that is the case in case of a ring algorithm. So now you know that the complexities, how the complexities are calculated, it is big O of n square. And uh, so this is all about in case of a leader election algorithm. So here if you have seen the concept that how exactly the leader election in the asynchronous and in a synchronous way. So when it is not possible and when it is possible, that is also discussed. When it is an infinite number of, if the n is known, then only it is possible. Okay, if the value of n is not known, then it is not possible. Okay, and similarly when in a synchronous node, when the execution of the processes is known, means it is in a finite time, then only it is possible. So these are the two possibilities. On the basis of that, this ring algorithm works and it is executed in a network. So now here I think we have seen what exactly the election. Okay. Mm, okay, so today I think we will conclude here. Just a wait, I download the attendance. So now be ready for the unit test 3 that we will conduct on Friday. Okay, I think we have a lecture on the Friday. No, we have a lecture on Thursday actually. Mm. Yeah, Thursday or Friday I will declare on the group, your WhatsApp group, and accordingly you have to do appear for the test. Okay, so now okay, now thank you so much for every um, thank you so much. So now you can log out your session.